What's up? In this video, I'm going to teach you about the halogenation of benzene. This is my first video I'm going to make about electrophilic aromatic substitutions. So this is what you want to do if you want to add a bromine to a benzene ring like this with Br2 and FeBr3, or the Fe, the iron, can also be aluminum. And you can also do this with chlorine too, with Cl2 and AlCl3. And not much places have this, but I also included the inorganic products. Isn't that cool? And this would be called the organic products. So, how does this mechanism work? So, I already drew some random stuff out here, so I won't take as long to show you how it works. So the first step is the formation of the strong electrophile. So this bromine thing and this iron tribromide is just sitting here. But this bromine here goes like this and attacks the F, because this thing is accepting electrons. And what is an electron pair acceptor? It's a Lewis acid. Okay. And so now there's a bond in between these two, like this. But look at that, it looks super cursed. But it actually is correct for some reason. And so since it's because of this, there's now formal charges on the atoms. So the Fe is minus charge and the bromine is positive charge, because bromine has 2 bonds and iron now has 4 bonds. Now after that, the next step is that, see how this is a positive charge? This makes it a strong electrophile, and this is very important to know. Now the next step involves the benzene, which will be the nucleophile. And the nucleophile will have its electrons in the pi ring attack this bromine over here. And then this bond electrons here will go into this positively charged bromine. And so now this and this will be together, or like this will be by itself and this will be stuck together by itself, and that will form a resonance stabilized uranium ion. Look, these electrons here are now attached to this bromine here, and so now there's no bond over here, and the bromine is here. And there's a positive charge down here because this carbon just lost a bond. So yeah, there's a positive charge here. And this uranium ion is resonance stabilized. As you can see here, I have drawn all the resonance structures because the pi bonds can like move around and the positive charge like moves around in these locations. This is also the rate determining step. I'll just say RDS, because this is the rate determining step because you're losing aromaticity. So now this uranium ion is at a higher energy than this thing right here. Now after this, you have this positive charge here. The last step is to reform aromaticity, and to do that you have to deprotonate something. So over here there is a secret implied hydrogen, the same with all these other places. And so this implied hydrogen gets stolen by this FeBr4, and it's specifically this electron bond here, and those electrons will go steal the hydrogen in like a elimination kind of type reaction. So the electrons from the hydrogen to the carbon bond will go down here and reform aromaticity. And it also forms HBr and FeBr3. And look, this is the catalyst because it was there at the beginning and it's reformed at the end. And yeah, so that's the mechanism. So as a summary, it works like this. So first, formation of a strong electrophile. Second, the nucleophile, the benzene, attacks the electrophile and it loses aromaticity. This is the rate determining step. And this causes the formation of a rhenium ion, which is resonance stabilized. Then it gets deprotonated to reform aromaticity and also the catalyst at the beginning. That's about it for this mechanism, and I'll see you in the next mechanism. Okay, bye.